41, 41, 41. So we did do 41. That's the one we
Yeah.
just did. All right. So we're up to 61. And 61, they want us to use the shell method. So one of our functions is the cosine of pi over 2x. Pi over 2, what? 61? Cosine of pi over 2x. And then we also have y equals 0. And this is for x's in between 0 and 1. And this is the region to be rotated. And the axis of rotation is 61, the y-axis. So this is what I was talking about at the beginning of the class when I said some of you thought you met the prerequisites but didn't, because some of you in your Calc 1 classes never learned to do this particular problem, which I can guarantee you that we'll be doing something like one of these volumes, not necessarily on this problem this soon. In fact, what we'll have to do is when we invent some new formulas for some new situations in chapters 8 and 9, we're going to be doing something very like this. But what it will do is instead of taking a region and rotate it, we'll take a curve and rotate it around an axis. And that will generate a surface for which we'll be finding surface areas and stuff like that. So it's really important that you've seen this idea before. All right, somebody want to tell me what to do? What's that? Draw a picture. Good idea. Draw a picture. What does the cosine of pi over 2x look like?
It's got to act like or like it's got.
What does the cosine look like?
It's a squiggly line.
Squiggly line. He's a helpful helper. Thank you, Mr. Helper. That's what the cosine looks like, right?
Yes.
What happens if you look at the cosine of some number, some multiple, times x?
Becomes a period.
All it does is change the period, doesn't it? It's going to be the same shaped curve. It's going to look just like that, but it's either going to be stretched out or squashed together. So that's what's going on here. The period is normally
2x.
2 pi.
2 pi.
The period in this case is 2 pi divided by b, isn't it? So the period of this thing, if we have the cosine of pi over 2x, that means that the period is 2 pi divided by pi over 2, so the period is 4. Right? Everybody with me on that? All right, so when we plug 0, why are we going to plug 0 into that? The region begins at x equals 0. So if I plug 0 into this, I get the cosine of pi over 2, which is,
Oh, 0, 0.
all right, so things got moved around. It's still going to be that shaped curve, but things have been squashed, right? This point has been squashed over there. So I know what to expect. I'm only expecting 1/4 of the curve, right? The curve looks like this if you break it into 4 pieces, which is what we do when we're learning the graph, right? There's that piece, then there's this piece, Then there is this piece. And lastly, there is this piece. Those are the four equal parts that you divide any sine or cosine into. We're getting 1/4 of that, aren't we? And it's starting at 0, so I'm expecting either that portion or that portion. I guess we'll find out in a moment. What happens if I plug 1 in there?
Be a pi root 2.
Oh, if I plug in 0, who said 0?
You did.
I
Should be
did.
1.
It's 1. But if I plug in
1.
1, then we get 0. So yeah, I guess we're getting this portion of it, aren't we? So y equals 0 is the x-axis. And since we're only going from 0 to 1, that is the region that we're rotating. And we're rotating it around y-axis. So if we take that region and mentally see what three-dimensional shape it sweeps out as it rotates around the y-axis, I guess what we're getting is some little, almost looks like a bullet, right? Something like that. The business end of a bullet. So, and they told us to use the shell method. Should we ignore them and go ahead and do the disk method? Would that be easier? Doesn't matter, does it? If they force you to use the shell method, you're forced to use the shell method. So since we're integrating around a vertical axis, what does the shell method mean we're going to have to do here?
Vertical shell.
That means we have to integrate horizontally. It's got to be an integral dx. The whole point of the shell method is to alleviate the deficiency of the disk and washer method. If you'll remember the disk washer method, if you have a vertical axis of rotation, you have to integrate dy. If you have a horizontal axis of rotation, you have to integrate dx. The shell method was invented to overcome that deficiency. It is what allows us to integrate at right angles to the axis of rotation. So if the axis of rotation is vertical, as is ours, then we must integrate horizontally. So I know it's going to be a dx integral. I know that I will integrate from the smallest x. By the way, the formula for the shell method is 2 pi integrals a to b, radius times height, and as we said, this one will be a dx integral. Radius and height of what? Of a typical shell. So what I'm going to do is first of all establish the limits of integration, small x to large x. And then I'm going to have radius times height dx. Radius and height of what? Well, I have to draw one of my typical little cylinders here. So what I'm going to do is somewhere from 0 to 1, pick an x, any x you want, and draw a line segment. Right? That line segment, when rotated, generates that little cylindrical shell. It's the radius and height of that shell that I want. Well, the radius, you can see, is an x value, isn't it? That distance is the radius, that's an x. So in place of radius, x. The height, however, is a y value, isn't it? Well, I can't keep y in there because it's a dx integral. So I'm going to rewrite this as 2 pi integral 0 to 1 x, and y is cosine pi over 2x dx. Would you guys all take a moment and write down what would this have been if you had used disk and washer? And if I see everybody writing and trying, I won't collect it in 5 minutes as a quiz. So crank out a piece of paper.